So I'll just say very kind of blanket statement. Most of these optimization problems are typically going to be there's some function typically of three variables that you're trying to maximize or minimize, and you're going to have to use some constraint to eliminate one of those variables. Then you'll have a function of two variables. Then you can apply the typical processes for finding the critical points and then see if you have a max or a min. It's very similar to how in 17a, you would often have a function of two variables that you're trying to maximize or minimize. You'd have to use a constraint to eliminate one of those variables, and then you'd be trying to maximize the function of one variable in the typical sort of way. So the hard part about this is typically the first part. Let's look at this first question here. I should write some things down here. Oh, pens. So day is still January. This is Co-17C. Let's look at this up. So let's look at this problem. We want to find the point on the plane x plus y minus z equal to 1 that is closest to the point 2, 1, negative 1. And yeah, I guess I could draw. I'll draw a picture here, even though I'm not thrilled about the picture I'm about to draw. Oh, I'm really not thrilled now. So here's my XYZ axis. And we're looking at the plane, x plus y minus z equal to 1. So the x-intercept is 1, the y-intercept is 1, and the z-intercept is negative 1. So we're over 1, down 1. So those are the three kind of points on the plane. Let's draw it in blue. Let's draw it in red. So there's part of the plane there. And then we're trying to find some point on this plane that is closest to the point 2, 1, negative 1. So we're 2 this way, 1 that way, 1 that way. So maybe like down about, let's say there. So whenever you're trying to find a point closest to a thing, or a point on a surface or a curve or whatever closest to some other point, what you're really trying to do is you're trying to minimize the distance between these 2 points. So what we're really being asked to do is here, we want to find the point on x plus y minus z equal to 1 that minimizes the distance between the 2 points. So the distance is given by the equation d equals to the square root of. Now, I should point out, I should use some labeling here before I start writing this equation. This point here is the point 2, 1, negative 1. And this other point here, we don't know what it is. So we're just going to call it x, y, z. Or you can call it a, b, c, or whatever you like. X, y, z is pretty typical though. So then the distance between these 2 points is just the difference in the x's squared plus the difference in the y's squared plus the difference in the z's. Instead of writing z minus 1, let's just write z plus 1. Okay, something that is always true. If you're trying to minimize a square root of a bunch of stuff, it is equivalent and easier to minimize just the inside of the root. Think about it this way. If you're trying to make this whole quantity as small as possible, you need to make the stuff you're taking the square root of as small as possible. Because it can't be negative, so by making it as small as possible, you'll make the output as small as possible. So instead, we're going to minimize d squared, which is x minus 2 squared. I should, sure, plus y minus 1 squared plus z plus 1 squared. I'm going to make a small change here, which is not that big a deal, but it's a big enough deal I'm going to make it. Instead of calling this uppercase d, I'm going to call it lowercase d because we use uppercase d for the thing we're going to do later with the second partial derivative. So let's call this a lowercase d. Sorry, that's kind of terrible to change in the middle here, but I'm doing there, lowercase d squared. And as I was mentioning, the thing we're trying to minimize at this moment has how many variables in it? 3. One too many. So we need a constraint. Luckily, they've already given us the constraint. We don't even have to come up with it ourselves here. The constraint is that point has to be on the plane. And the equation of the plane is x plus y minus z equals 1. So take your pick, isolate one of those 3 variables. Z is the usual choice. I don't see a reason not to pick Z here. Sometimes it's better to choose one of the other 2 things. Like I think there was a problem you're doing last class where I decided to isolate either X or Y instead because it was just a slightly nicer choice. So we're going to take this equation and we're going to say, great, Z equals X plus Y minus 1. So now we're going to plug that in for the Z right here. And we'll get that D squared is equal to X minus 2 squared plus Y minus 1 squared plus X plus Y minus 1 plus 1. Let's just cancel those ones real quick and say we have X plus Y squared. Right, I plugged in X plus Y minus 1, but then the plus 1 cancels the minus 1. So now we're going to do the usual thing. We're going to find the partial derivative, set them equal to 0, find our critical points, and then I think we should probably check if it's a minimum, although really you couldn't maximize the distance, right? Because if you found a point, right, this plane, right, I know I've only drawn a little triangle of the plane, but this plane is infinite, right? It's kind of like saying, take this point on the floor and find a point on the wall which extends infinitely in the up, down, and left, right direction that is the furthest away from it. Can't do it, right? You can keep finding points that are further and further away. On the other hand, I can definitely find a point on the wall that is close to this point here. It's probably that point right there. Sorry for those of you on Zoom, you can't quite see that, but I think you can probably imagine it. So that's what we're going to do here. We're going to find the point that is the critical point, and then it's probably just going to be the closest by default. So let's take our partial derivatives. Yeah, I'm going to call this, let's just call this F. This is my F of X comma Y. So then Fx is going to be 2 times X minus 2 to the first times 1 plus 0 plus the derivative of X plus Y squared is going to be 2 times X plus Y to the first times 1. And then similarly, Fy is going to be 2 times Y minus 1 plus 2 times X plus Y. I will kind of point out here, it's not really worth your while to multiply these out first. Like, there's no good reason to multiply X minus 2 squared as X squared minus 4X plus 4 or that or that. It's easier to take the derivative as is. So I would probably divide both sides by 2, I guess, just to get rid of those 2's. So this is X minus 2 plus X plus Y equal to 0. Let's isolate a Y here and get a Y on the left equals a negative 2X plus 2 on the right. Similarly here, we have a Y minus 1 plus X plus Y equals 0. And I guess I'd probably end up isolating X here. So I should back up a little bit. The reason I jumped straight to isolating variables is because I could see from the get-go that I wasn't going to get like an easy solution for X or Y here. Because I was going to have to solve for one and then plug it into the other thing. Here, I guess I really should stop myself from doing too much work. Let's just simplify this and say we have 2Y plus X minus 1 equal to 0. And then instead of isolating X, which isn't really going to get me anything new, I'm just going to take this and plug it in for Y over here so that I can solve for X. So I'm going to get 2 times negative 2X plus 2 plus X minus 1 equal to 0. So that's going to be negative 4X plus 4 plus X minus 1 equals 0. That's a negative 3X plus 3 equals 0. We're going to get X equal to 1. And if we plug that back in over here, Y is going to equal negative 2 times 1 plus 2, which is 0. So my critical point is 1, 0. We can check it will be a minimum. Let's go ahead and check it. I think it's worth checking. So we're going to find our fxx. It's going to be 2. Let's actually, yeah, fine. Our fxx is going to be 2 plus 2. Wow. That's how you write the number 4? No, it's not how you write the number 4. Well, sure. There you go. fxx is 4. Sorry. Fyy is also going to be 4. And then fxy is going to be 2, I believe. So then calculating d, it's going to be 4 times 4 minus 2 squared, which is 16 minus 4, which is 12, which is positive. We know we have a max or a min, not a saddle. And then since fxx is positive, that means we are concave up, which means we have a minimum. Now we have to be a little extra careful here because although we found the critical point where x is 1 and y is 0, we didn't actually answer the question. Because if you look back at the question said, find the point on the plane, which should have not just an x and a y coordinate, but also a z coordinate. So we actually have to go back and say, okay, well, we know that z is equal to x plus y minus 1. Sorry, you can't quite see that. Z is equal to x plus y minus 1. So finding the z coordinate here, z is equal to x plus y minus 1. So z is equal to 1 plus 0 minus 1, which is equal to 0. So our point that is closest is going to be the point 1, 0, 0. Which feels a little disappointing. It just feels like it's not very interesting, but that's probably because it was easy to come up with. So looking back at our picture here, the point on the plane that ended up being closest was this point right here. That point is the point that is closest to that point over there. And when it's probably, my picture is probably not doing a very good job of displaying that. Yeah, sure, why not? Let's go ahead and look at that. I feel like it's worth looking at here just for a second. So if we look at Desmos, Desmos 3D, I think. So one of the downsides of getting older is your eyes do start to need corrective vision, apparently. I might be getting close to that point, which is disappointing for someone who's always had perfect vision, but I'll live. But I won't be able to see if I don't do something about it. Sorry, I forgot the equals there. So there's my surface there, x plus y plus z equals 1, which I did not do. Oh, sorry, yeah, which, right, kind of. So like, here's a little triangle part of it that we drew here, kind of. And then if we look at the point 1, 0, 0, you can kind of see, oh, sorry, sorry, not that point. And then the other point, which was 2, 1, negative 1, stop moving around. So hopefully you can maybe let's zoom in a little bit, James. So hopefully you can kind of agree that, oh yeah, if you're looking at that plane there, the point that's closest to it is the point on the plane that's closest to that green point is that blue point, right? Yeah, there's not, yeah, I don't, I'm trying to remember how you draw a line, but I don't remember at the moment. So basically the line that would go through that plane perpendicularly through that blue point will exactly go through that green point, which is the way you find the closest point. It's the one that has to be perpendicular to it. Hopefully you can kind of see that. Yeah, kind of. Yeah, okay, anyway, enough of that. So let's do one more optimization problem, and then we'll talk about these absolute maximums. So this one was, in my opinion, a little easier than usual in that the constraint was kind of already given to you. Let's look at one where that's not the case. And I think this is problem number 35 from section 9.6, just because it looked reasonable-ish to do. So here's the setup. This is 9.6, number 35. Yeah. Yeah, of course. What do you want to see? You're welcome. So 9.6, number 35 says a cardboard box without a lid is to have a volume of 32,000 cubic centimeters. Find the dimensions that minimize the amount of cardboard used. Okay, so we have an open top box. Draw something like this. There's our box. And we don't know any of the dimensions, the base, the width, or I feel like there's like people sometimes say base, width, depth, whatever. We don't know the width, the depth, or the height. So we're going to call them X, Y, and Z. And we have two things going on here. There's something we want to maximize. We're trying to, something we want to minimize. We want to minimize the amount of cardboard, aka the surface area. So minimize surface area, and that's going to equal the base area, which is X times Y, plus the front rectangle, which is X times Z, plus the back rectangle, which is also X. Let me draw the rest of this part that you can't see here. All right, so we've got the back rectangle, which is also X times Z. So we have two X times Z's. Similarly, we have a Y times Z on the right and a Y times Z on the left. So we have two Y times Z's. And just like last time, the thing we're trying to optimize is a function of three variables. So we need a constraint. And here the constraint is the fact that we want this box to hold 32,000 cubic centimeters. So we're going to say that the volume, which is equal to X times Y times Z, should be equal to 32,000. And then you can isolate any one of those three variables in this constraint. Again, the typical choice is picking Z. So we're going to say that Z is equal to 32,000 divided by X times Y. It might end up being nicer to write it as 32,000 times X to the negative first times Y to the negative first. We'll see if that's helpful. So then we're going to plug that in to the thing we're trying to minimize, so it becomes a function of two variables. So let's see what we've got here. The new surface area equation is going to be surface area equal to X times Y plus 2 times X times 32,000 over XY plus 2 times Y times 32,000 over X times Y. And before we find any partial derivatives, we definitely do want to simplify this to make our life easier. So I should definitely cancel an X here, cancel a Y here. And I do think I want to bring those other things up to the numerator so it's easier to differentiate. So I'm going to say that my surface area, which now let's just write it as a function of X and Y, is going to be X times Y plus 2 times 32 is 64, so 64,000 times Y to the negative first plus 64,000 times X to the negative first. I will again make the observation I made in previous examples. This equation is symmetric in X and Y, meaning our critical point's probably going to be one where X and Y are equal to each other. So let's find our partials. Fx is going to be Y plus 0 plus negative 1 times 64,000 times X to the negative 2, or minus 64,000 divided by X squared. Right? The root of this is 64,000 times negative X to the negative second, and just brought that X to the negative second down to the bottom as X to the positive second. And almost exactly the same, our Fy is going to be X minus 64,000 times Y to the negative second, or 64,000 divided by Y squared. I'm going to set both of those equal to 0. This, yeah, I don't love this, but it's fine. So to be extra super careful here, we have to be careful in that we don't want to cancel anything kind of weirdly. I'm just going to isolate one of these two variables. I'm going to isolate Y. I'm going to say, great, Y is equal to positive 64,000 divided by X squared. And I'm going to plug that in for Y over here, which I know is going to be kind of gross, but oh well. So that means we're going to get that X minus 64,000 divided by 64,000 over X squared is equal to 0. All right, let's make this look less terrible. So dividing by a fraction means we multiply by its reciprocal. So we could rewrite this as x minus 64,000 times the reciprocal of this is going to be x squared squared, which is x to the fourth over 64,000 squared. I can cancel one of those 64,000s. Oh, sorry, still equal to 0. And now I'm left with x minus x to the fourth over 64,000 equal to 0. Let me ask you all a quick question. What's one easy solution to this equation? What could you plug in for x and for sure get a correct answer? 0. Is 0 the right answer? Definitely not. If we look back to the right, we're talking about finding the dimensions that minimum. Like, I mean, okay, fine. No. Sorry, 0. I should actually point out here in this case, not only is 0 not the right answer, even though technically it would minimize the surface area, but 0 is not the right answer because it's not in the domain of the original function, right? Our volume needs to be 32,000. So getting z equal to 32,000 divided by xy means x can't be 0. It is not in the explicit domain of the original function at all. So 0 is not even an option. So let me point out two ways you could solve this. One way you could solve this, which is maybe feels a little bit less like more work, is factoring out an x and saying you have 1 minus x cubed over 64,000 equal to 0. So then you're just going to set this part equal to 0. And you're going to say 1 minus x cubed over 64,000. I feel like you should be able to jump to just say, great, x cubed has to equal 64,000 here. You could also do more work and bring this over and multiply by 64,000. So x cubed has to equal 64,000. X is going to be the cube root of 64,000. Cube root of 1,000 is 10. Cube root of 64 is 4. So the cube root of 64,000 is indeed 40. Or if it made more sense to you, you could have done this. You could have brought this over to the other side and said that x is equal to x to the fourth over 64,000 and then multiplied. And then even though it's kind of not the best, you could divide both sides by x here. Usually I frown upon that, but since we know that 0 isn't really an answer, we don't have to worry about it so much. And then you get to the same place. Okay, so we got x equal to 40. And then let's go ahead and find y. So I'll remind you, there's your y. So y is going to equal, okay, here's a better way to write this. Instead of 64,000 divided by 40 squared, let's write it as 40 cubed over 40 squared. Right, we know that 64,000 is 40 cubed, and then that's just going to be 40. Also, we were already pretty sure that x and y had to be the same anyway. And then we will find z. I'll remind you that z was equal to 32,000 divided by x times y. I feel like, no, that's right. I just feel like I'm, okay. So that's going to be 32,000 divided by 1,600, which is going to be 20. I'm not of a mind that we should check to see that this is a minimum. I think we should just buy it. So the dimensions are a 40 centimeter by 40 centimeter by 20 centimeter high box. Let's look at, yeah.
So um, you plugged in like into what equation with the
So to find z or define y. Okay, so to find y, I used this right here. Right, I used essentially. So remember, I so if you look back at our partial derivatives, I have these two equations, right? So really, I found x equal to 40, and then I had to plug 40 back into this equation to find the other coordinate of my critical point. So I should say my critical point for my function is x equal to 40, y equal to 40. We did not do the work of checking to see that it gave us a minimum. Just going to buy it. And then we said, great, we still have to find the z coordinate because they wanted all the dimensions of the box. Then we went back to this equation up here and said, oh yeah, z is equal to 32,000 divided by whatever x times y is. So then we divided by the x times y to get the z value of 20. So usually when you're going back and finding the other things that are left still, the equation should already kind of be in your work because you kind of had to isolate z and isolate y to get to the point where you can solve for x. So usually they're already up back in your previous work. Okay, let's look at some absolute min and max values on closed boundaries. And just make sure I make the right thing. Yeah, looks good. Not you, not you. There we go. 1 second. Sure. Okay. So, we're gonna look at an example, and I'm gonna not draw some pictures, but just show you some pictures. So, absolute, maxima, and minimum values on a closed boundary. And typically, when someone says a closed boundary, what you should think of is a region in the XY plane in two-dimensional space that includes the boundary. If you don't include the boundary, so the word closed means you're including the boundary. If it's an open domain, you're not including the boundary. And the definition is a little bit more technical than that, but as far as we're concerned, that's what really matters. Closed boundary includes the boundary, just like a closed interval with brackets includes the endpoints, and an open boundary excludes the boundary, or an open interval excludes the endpoints. So let's look at this example. We want to find the absolute maximum and minimum values of, yeah, we'll do this one first. F of xy equal to x squared plus y squared plus x squared y plus 4 over the region given by D equal to the set of all points x comma y such that the absolute value of x is less than or equal to 1 and the absolute value of y is less than or equal to 1. Or in other words, the square where x and y are both between -1 and 1. So I'll point out that our region D looks like this. Here's our region D. The corners of D are the points 1, 1, 1, -1, -1, -1, and -1, 1. So I'm not going to draw these next pictures because I'm not really good at drawing them, but I'll show them to you. So here's the idea. On the essentially above this region, there's some surface. I kind of like to think of like a blanket or a waving flag, maybe. And that surface could have a lot of different shapes. It could look like something like this, where you can clearly have some sort of absolute maximum in the middle and an absolute minimum kind of on the boundary. Not that that's really super important. So maybe it looks like that. So there might be a critical point in the middle of your region that we have to test. But your surface could look like that, where your absolute maximum highest point on the roof of your house is what I'm really thinking. I think of this like the roof of a house, could be up in that corner, and the lowest point could be over in that corner. So the corners are also potential candidates for where we have an absolute maximum or minimum. Or your surface could look like this, where you don't have a maximum or a minimum in the middle, but in the middle of one of the edges or boundaries, you do have an absolute maximum. And in the middle of this boundary, you have an absolute minimum. So there are three different regions or parts of the boundary we have to look at. You have to look at the points in the middle of it. You have to look at the corners, and then you have to look at the edges of each boundary and see where you might have a maximum or minimum there. So that's what we're going to do. I think in class he did not talk about the corners really, but usually you have to check the corners in some way, shape, or form. So we're going to do all three of those things. The first thing we're going to do first is we're just going to find critical points in the usual way. I'll point out, none of this is going to happen generally, but if for example, we got a critical point that was, I don't know, say 2, 0, that would not be something we worried about because 2, 0 isn't in the domain that we're looking at. So the critical points you get have to be in the domain we are looking at to be valid. Just like back in 17A when you found absolute maximum or minimum of a function on the closed interval, if you have points outside of that interval, we did not consider them. So critical points, usual process. Fx is 2x plus 2xy. Fy is 2y plus x squared. I'm going to deal with the first equation because it doesn't have any squares and I can factor out the 2x. Excuse me. That's going to give me 2x times 1 plus y equal to 0. So I either get x equal to 0 or y equal to -1. Plugging either one of those into the other equation, if I plug in x equal to 0, I get 2y plus 0 equal to 0, which gives me y equal to 0. So I have 0, 0 as a critical point. So right there, right smack dab in the middle. And then if I plug in y equal to -1, I get -2 plus x squared equal to 0, which leads to x squared equal to +2, which leads to x equal to plus or minus the square root of 2. And my other critical point would be, I should say points, would be plus or minus √2, -1. However, square root of 2 is bigger than 1. So I'm looking at a point like here and here outside of my region. So I'm not going to worry about those. Not that they're not critical points. They tend, like if on a different note, if you're like finding the relative extreme of this function, you would totally use those points as well as 0, 0 to classify whether you had a maximum or a saddle. As far as we're concerned, we don't care about that. And then, yeah, any more room here. So then the second part, find the critical points along each boundary. Okay, let me ask you all. How many boundaries are there? Yeah, I haven't defined it very well, but yes, there are 4 different boundaries. That one, that one, that one, and that one. And they all have equations. They're usually just lines. This top boundary is y equal to 1. This bottom boundary is y equal to -1. This right boundary is x equal to 1. This left boundary is x equal to -1. So what we're going to do is we're going to use those. So let's start with y equal to 1. I'm going to go up. So if I say y equal to 1, well, then my function is going to become the following. It's going to be f of x comma 1 equal to x squared plus 1 squared plus x squared times 1 plus 4. I will point out, if we're on the line y equals 1, y is a constant. Y is never changing. So it wouldn't make any sense to take the partial derivative with respect to y, because it's going to be 0 if y is always 1. If y is never changing. But we are going to take the partial with respect to x. So the partial with respect to x here is going to be 2x plus another 2x. So that equal to 0, you're going to get x equal to 0. So that means that the point 0, 1 is also a point we're going to consider. I'm going to redraw my boundary over here. I don't usually like to shade in my boundary. I know I did, but I don't usually like to. I like to draw it like this. So here's my boundary. So far I've got the points 0, 0. And then my corners, of course. And then we just found out that x is 0 and y is 1 is also a point where we could have an absolute maximum or an absolute minimum. Continuing on, y equal to -1, we're gonna get the same sort of result. If we plug in -1 for y, we still have x squared plus -1 squared plus x squared. Oh, we might not get the same result actually, plus 4, is that right? And taking the partial derivative, we're gonna get 2x. I should have just canceled this out really, because x squared minus x squared is 0. So the partial derivative here is always 0. What does that mean? If the partial derivative in the x direction is always 0 along this line. What that means is, on that line, if you move in the x direction, the derivative is always 0. Meaning that essentially it's, well, in fact, if I was smarter about this, I would look back at the original piece, and when I plugged in y equal to -1, we're getting 1 plus 4, which is 5. It means the original function there, at least on that border, is constant. So we don't really have any extra critical points there. We're still going to end up checking the endpoints though. And then we're going to check x equal to 1. So plug in 1 for x, I get f of x comma 1. Anyway, covered up, sorry, not x comma 1. 1 comma y. Go back to my function here. That's going to equal 1 squared plus y squared plus 1 squared times y plus 4. Take the partial derivative. Now with respect to y, and we get 2y plus 1 equal to 0. So we get y equal to -1/2. So we get 1 comma -1/2, which is right there. You don't really need to draw them on your region. I just like to. I think it's useful. I think it's useful. I couldn't really say why I think it's useful. I just feel like it's useful. And then maybe it's useful for making sure that the points you're plotting are actually in the region and not out of the region. And then lastly, x equal to -1. We're going to have f of -1 comma y, which is going to be 1 plus y squared. Sorry, yeah, no, still 1 plus y squared plus 1 times y, because -1 squared is still +1 plus 4. And so when we take the partial, we're still going to get the same result. We're going to get fy equal to 2y plus 1 equal to 0. You see y equal to -1/2. So our last critical point is -1 comma -1/2. So it looks like we have 1, 2, 3, 4, 5, 6, 7 points we have to plug into our original function to see what our absolute max and what our absolute minimum is. I do think you have to check the corners. If your teacher says otherwise, well, then go with that. But as far as I know, the corners, I suppose no, I think you have to check the corners. Anyway, let's do it. Oh, question. Correct.
Then we're looking at every point of x point. Since we put y equals 1, y equals -1.
Right, so along the line y equals 1, we might have an absolute maximum right in the middle at 0, 1, because when y equals 1, the derivative in the x direction is equal to 0 when x is equal to 0. So it's kind of like this shape right here, right? Along the line y equals 1. Sorry, this is labeled poorly. Pretend like it's labeled the other way just for a minute. Along the line y equals 1, you're getting x equal to 0. You might have something like this where the derivative in the x direction is 0. The derivative in the y direction is not, but we're not moving in the y direction. So that's why we're looking for on this boundary right there, there could be an absolute maximum or an absolute minimum. So that's kind of the idea behind why we're looking for all these points along each border or edge. Right, the corners are always candidates for being an absolute max or minimum, just like way back in 17A, if you had something that looked like, you had something that looked like this, and you did it on a closed interval, well, that could be an absolute maximum, or that could be an absolute minimum, or that could be an absolute maximum because it's the end, and that could be an absolute minimum because it's the end. So you always have to check your ends, which are your corners in this case. So looking back at our points here. So our function again, a reminder, our function was, what was our function? X squared plus y squared plus x squared y plus 4. And we're going to check all 7 of these critical points. Just be smart about this. So we're going to do f of 0, comma 0 is obviously 4. And then just kind of go through the list in whichever way feels the best. F of 1, comma 1 is going to be 1 plus 1 plus 1 plus 4, which is 7. F of negative 1, 1 is going to be 1 plus 1 plus 1 plus 4, which is 7. F of negative 1 is going to be 1 plus 1 minus 1 plus 4, which is 5. F of 1, negative 1 is going to be the same. It's going to be 1 plus 1 minus 1 plus 4, which is 5. Those are the easy ones. Now for the slightly harder ones with some fractions. Oh, let's do f of 0, 1. F of 0, comma 1 is going to be 0 plus 1 plus 0 plus 4, which is also 5. Now finally for the last two here, f of 1, comma negative 1 half is going to be 1 squared plus negative 1 half squared, which is 1/4, plus 1 squared times negative 1 half is going to be negative 1 half plus 4. It's going to be 5 plus a quarter minus a half is minus a quarter. That's going to be 4 3/4. 4.75. And I think it's the same when you plug in negative 1 half. Because you're still going to get negative 1 squared plus negative 1 half squared. But then you're going to have still 1 times the negative 1 half, which is a negative 1 half plus 4. And you get the same thing. So looking at all these numbers, which of those 7 numbers is the largest? Right. So we have absolute maxima at both 1, comma 1 and negative 1, 1. And then we have absolute minima, and I do think we have 2 of them, at 1, comma negative 1 half and negative 1, comma negative 1 half. Curious about something here. So let me just show you here. I think we can graph this in an interesting way here. Yeah, calm down. Let's see if we can graph this because I would kind of like to show you what it looks like. Well, I should say, let's see if we can graph it and then limit the domain. So we have x squared, we have z equal to x squared plus y squared plus x squared times y plus 4. Okay, let's stop moving around. Cool. So that's not super helpful. I think we'll find out here. I think we can do this thing where we limit the domain. Let's see here. We want x to be between negative 1 and 1. And we also want y to be between negative 1 and 1. We'll see if this works. Cool, it worked. Kind of. It kind of looks like, maybe it's, I don't know. I feel like it didn't really work. I was hoping it would work. Yeah. Okay, here's a better way to do it. Let's just do this instead. So we'll just cut it with the planes. X equals 1. Yeah, and we'll extend that in a second. X equals negative 1. Y equals 1. Y equals negative 1. And then we can click on these things here. Zoom in a little bit. So we're looking at this. Ooh, come on. Sorry, I'm ruining it. So we're looking at that kind of red surface that's just in the middle of that. Oh my God. Sorry. I feel like I'm really jacking it up here. You can kind of see it in there and maybe a little bit. And then I'll just plot one of these points. If we plot the point, say 1, 1, 7, you can see, oh yeah, look right there. Maybe. It's the highest point on the surface that is in that square. You can kind of see, maybe. You're like, yeah, James, sure, maybe, kind of. Yeah. There should be a way to do this better, but I didn't think about it ahead of time, so I don't know what it is. I'll work on it though, see if I can make something nicer on this later. I think we probably don't have enough time to do another example, but I'll say, so it looks like the examples of this in the textbook are pretty, I would say they're pretty, oh, you know what? This is literally one of the examples in the textbook. This is number 19 from the textbook. Interesting. Okay. The other examples in the textbook, I think, are also fairly straightforward. On Friday, we'll try and do one where the region is triangular because so I'll point out in Grant's notes, not on this section, but in his section about, oh no, that's a different thing. Never mind. We'll do a triangular one on class because for the triangular region, the border that isn't like a horizontal or a vertical line, you actually have to find the equation of that straight line. It's usually not too hard, but then you're subbing that in for the other variable. So it's a little bit, it's a slightly more complicated, but not really that much more complicated. All right, that's all I got. I have office hours right now, and then I'll post the solutions to the practice exam tomorrow. I highly, 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 highly recommend doing it on your own before looking at the solutions. And I'll see you on Friday.